Today I will talk about a particular way to represent or to model or to think about machine learning problems. Since I started at Aalto University in 2015, I have taught the biggest courses on machine learning at Aalto. I would say in total some thousands of students. I have supervised tens of theses, bachelor thesis, master thesis, some PhD thesis in the field of machine learning. And since it's a very vast field, machine learning, I needed to come up with a way to bring everything together, to find a common framework. And the result of this researching for such a framework was these three components of machine learning. So first, the pointers for background material. So this presentation is based mainly on my textbook that I have written up during teaching the courses on machine learning, which is available on Archive for free. If you want to dig deeper, there's this Deep Learning with Python book, or there's the Deep Learning book on more technical details and on a higher level. So if you're not interested in the theoretic details or mathematical details, then this Deep Learning with Python book is the right guide for using machine learning or deep learning. Okay, so I always think about machine learning as something very practical. So machine learning methods and deep learning methods are something that are around our everyday life. And we always should think about how can we use a machine learning method for some problem. For example, I guess many of you have now this slight paranoia. If somebody coughs or sneezes and you want to immediately know, is this a corona case? This is a machine learning problem, and we can formulate this as a machine learning problem in a way that I will now discuss in detail. So, as already announced, this formalization of machine learning methods is based on three components. You can think of these components like building blocks. And for each component, we can have different options or design choices for the corresponding building block. And we can combine the different components in I would say, infinite amount of combinations. And these different combinations of these blocks are different machine learning methods. One particular combination of these three blocks is linear regression. Linear regression is still maybe the most important machine learning method there is. Another combination is deep neural networks. And I will discuss a bit more about this type of combinations today in particular to help the students for the course Deep Learning with Python. But the principle of thinking about three main components is the same for all machine learning methods. And deep learning methods are just a subset that correspond to particular choices for these building blocks. So let's look at the first component, data. It might seem very intuitive what data is, but if you have to come up with a definition, what is data, you might struggle. It's not trivial if you really want to nail down the precise characteristics of what we talk about when we speak of data. And I have found the most general sense of using data is in the sense of having a large set of data points. So data is something that consists of a large pile or a large set of similar pieces or atomic units, which are called data points. So data points could be, for example, cows. So one cow, one particular cow is one data point. This cow here is one data point. This cow here is another data point. So we have several cows, and this gives one data set. Okay. Another example, one data point represents one forest. So different forests are different data points. And we get a data set by having a bunch of forests. Another example, a bit more abstract, a data point could be a particular day. For example, a day during a pandemic. So these are days that are in the March 2020. So one day is one data point and several days constitute one data set. Yeah. So machine learning methods or deep learning methods always need many data points. If you only have one single data point, then there's not much you can do with machine learning or deep learning methods. These methods use averages over a large set of data points. Okay. Yeah, please ask questions on the fly in the chat. Yeah. So let's continue. Or recap, a data point is a highly abstract concept. A data point can be anything. The important thing is that this anything, this object, can carry information. So it can be take on different values or something, like a cow. A cow can have different properties that distinguishes it from other cows. So a data point is something that can tell us something, that carries some information. So data points can be persons, data points can be random variables. So data points can be mathematical concepts or mathematical objects. Data points can even be machine learning problems. And this might seem completely pervert, but this is how you model or how you could model meta-learning or learning to learn methods. In meta-learning methods, we consider data points being machine learning problems, and we want to learn machine learning methods that learn machine learning methods. I will not dig further into this in order to not confuse it too much. I just want to make the point here. Data point is a highly abstract concept, which makes it very versatile. So you can model any aspect of your daily life, and we will force you, we will push you to model everyday aspects as machine learning problems in the student projects. So this is exactly what the student projects are about, that you think about one particular aspect of your daily life, like going to the bus, playing tennis, or writing an essay. Any aspect of your daily life where you can think about what could be data points, what could be a large set of similar units. For an essay, writing an essay, data points could be individual letters. So you have a lot of letters. Okay. As I said, a data point is something highly abstract, and you typically you can never grasp a data point completely. It's, for example, when we use this data point one day during a pandemic, then this data point in principle contains every information corresponding to one day during a pandemic. And every information in the extreme case means all the states of all molecules or all atoms in the universe. This defines one particular day. So we never have full access to a data point. We only look at data points via some window, I would say, kind of as a picture. And this window, which we look at data points or by which we measure data points, are called features. So we don't know everything about a certain data point, but we know some features. Yeah, there was one question in the chat, a very good question. What could be these properties for the examples I have mentioned? So what could be features for a cow? What could be possible features of a cow? So a data point is a cow, and the features or the properties of a cow could be the weight, could be the amount of milk it gives per day, could be the breed, could be the age. Yeah, I see it here on the chat, you name it. Yeah, so we find some features. Other example, the forest. Features of a forest could be the number of total trees in the forest, or the average temperature during a year in that forest. Okay, so we find typically a lot of features, and often we have so many features that it's difficult to know which are the relevant features. So we have to select a few features, which is called feature selection. Okay, so this is one type of properties. Features is everything that we can measure or count or compute easily. Anything that can be measured by a simple device like a thermometer to measure temperature. This is a feature. But then a data point typically also has other properties, which we call label. And labels are different type of properties, which often mean higher level facts or quantities of interest. And they can either be determined only in hindsight, so if we know already what happened exactly, or they require human experts. So let's look at the examples again. What could be a label, a property of interest of a cow? So a data point is one particular cow. What could be a quantity of interest that we cannot measure easily by hardware? Yeah, the quality of the milk it will give, the nutrition, or the life expectancy, or how much revenue it will bring over the whole lifetime to the farmer. This is something we cannot measure easily. This is something for which we need experts like agriculture economists. They're experts for this. However, what machine learning is about is try to imitate this expert knowledge. Try to find a mapping that reads in the features, so the weight, the size of the cow, so we can put it easily on a scale maybe. There are these big scales where you can put the cow on top and it tells you this cow has 600 kilograms. And then we could also take a picture of the cow. This is also a feature. We take just a picture, and then we could train a machine learning method or a deep learning method by using labeled data points. So by using data points or cows for which we know what was the life expectancy in hindsight, to learn a mapping or to learn a predictor from features to label. Yeah. Okay, another example. What could be a quantity of interest? Yeah, cow happiness is also a potential label. Yeah, you can choose what the label is. In the project, in the student projects, I want you to write down in the report, what do you choose as a label of a data point? And this could be very well, you could say a data point is a cow, and I use as a label cow happiness. Okay, another example, a forest. So let's say a data point is a forest. So we know what features could be. Features could be number of trees, the types of the trees, or the average temperature, or is there a lot of snow, precipitation during winter? What could be a quantity of interest for a forest? So air quality properties. Yeah, the risk of having a forest fire there, very important in particular when you are in California. You want to tell for this particular forest or neighborhood, there's a risk of 90% of having a forest fire. While for this other forest, there's a risk of only 10%. So how can we get, yes, yeah, there's one comment, label is the goal, is our goal for modeling. Yeah, so we model the data point by defining what the label is. So, but let's stick to this example where we say the label of a forest is the risk of it having a forest fire. How can we get labeled data points? How can we get examples of forests for which we know the risk for a forest fire? Who could tell us this? Who could have such knowledge? Who would you ask? Historic data, we can look at the media messages. There was a forest fire, so we know it in hindsight. But is there another way? Yeah, weather station data is I would say a feature. So we know the temperatures, around temperatures. Yes. So we would need subject matter experts, and there are experts for how forests behave and what the risk is that they catch a fire. Okay. So this is a key challenge in machine learning and in deep learning methods. You need to get labeled data. So although you can define whatever you want as label, like the cow happiness, the usefulness of such a definition also depends to some extent on how easy can you get labeled data. Okay. Yes, so satellite images could be used, for example, to get features of the forest, like to see how much green is there in the forest. Is it very green or so? Yeah, and by the way, which one of you knows Amazon Mechanical Turk? So this is called Amazon Mechanical Turk. I write it in the chat. If you want to look it up in the internet, this is a service where you can buy labeling time. So you put data points there, like images, and you ask them, or you offer some money, some 10 euros per hour that you pay to anybody which looks through these images and tells cat or no cat. Yes. And if you have time, so you can sell your time to do labeling via Amazon Mechanical Turk. So that's one way to get labeled data. And you have it to some extent under your control how difficult it is to get labeled data, because you can choose what you use as a label. So if it's very difficult to get labeled data for some choice for the label, it might be a good idea to use another choice for the label. Okay. Yeah, here another example for a hiking trip. So you take a data point, could be somewhere in the mountains, and this somewhere in the mountains has features in the form of the pixels of a snapshot. And what you would like to know, the label is the hiking duration to reach the peak. And the hiking duration should take into account your personal condition at the very moment when you start the hike. So no average duration, but how much does it take you today to reach this peak? Okay, yeah, and I have put there more examples. The more examples you look at and think about, the better. So to understand this concept, or how to use these concepts of data points, features, and labels, in my experience, the only way to learn this is by practicing it. So try to think about every aspect in your everyday life. How could we model it as data points? How could we model it? Or what are the features of the data points? What is the label? For example, a data point could be some ski day ahead. This was 2 years ago, a nice winter day. I took a picture outside of my window. So the data point was some ski day, some particular day. The features that I had was a snapshot in the morning, and maybe also the morning temperature, and also the weather forecast. So the weather forecast that you get from online services is are features, because these are not the true labels. This is a forecast. But this is also something you can use as a feature to predict the label, which could be the maximum daytime temperature. Knowing the maximum daytime temperature is important to choose the right kind of wax for your ski. And choosing the right kind of wax for your ski, for those who are not familiar with cross-country skiing, is very important to have a nice experience. Okay, yeah, here are more examples. We have biology, we have city planners. City planners want to know, how do people move on public spaces? This we can model as data points and features and labels. Yeah, so there's one comment. So the features could be anything that is related to the conditions of data points. Yes, so this is an important point. Features and labels are design choices. You can choose whatever you want as features and labels. It's up to you, it's a definition. You can, my mathematics professor, when I started in Vienna, always used to say, you can define whatever you want. It just needs to make sense or be useful. So you can define or use as features and labels whatever you want. You can use cow happiness as the label, but you must think about, can you get easily labeled data? And also, if you define features, can you measure them easily? So a feature should be something that you can measure, collect easily by computers or software. The prime examples for features is always, in my case, a picture. So I can take easily a snapshot with my smartphone, and the red, green, blueness values of the pixels are features of the object that I take a photo of. But there are many, many other choices for features. But when you formalize a machine learning problem, you must write down, what do you use as features? What do you use as labels? So this is the key challenge, or the key aspect of the student projects. When you compile the report, I want you to write down, what are data points? What do you want to use as features? And what do you want to use as labels? Okay. Yeah, so there's one question, is there any limit on the number of features and labels? No, theoretically, no. But practically, yes, because the more features you have, the more you have to compute. But in theory, no, you can use, as I said, you can use as features for one particular day all the state of every atom in the universe, in principle. But can you measure this easily? No, so it might be not a practical choice. Yeah, you can also use, there's a good comment, if a deterministic predictor calculates a label, or if a predictor, like a deep learning method, computes a prediction, this is also a label. You can also use this as a label for some follow-up or improved method. Like in this example, in this weather forecast, so we can use the forecasts or predictions obtained by a weather predictor, for example, used by Google. We can use this also as a feature for our own tailor-made prediction method. Yeah, so excellent comment. Big numbers using too many features might distract the machine learning method. So using more features than you really need, or irrelevant features, can result in a deterioration of the quality. And you will see this in round 4, I think, or also in round 2 might be. You will see this in round 2 of the machine learning course, where using more features makes the accuracy go down, actually, which is counterintuitive, because you would think the more features, the better. But one student here made a very good comment and pointed out that using too many features can distract or confuse the machine learning problem or the machine learning method, because it must invest too much computational resources in looking for the relevant features, such that it has not resources left to exploit the important features enough. Yeah, so then another question, is there a famous database of already labeled data? Yes, so it's now also a big contribution to research to compile databases labeled data points. Yeah, you can publish a paper just by describing a database of labeled data, and one such example is called ImageNet. I write it here in the chat. So ImageNet is a database containing billions, I don't know, I think billions of images of animals or people. Okay, so but now let's check the time, because we have 3 components, and if I divide the lecture evenly, we should now move on. Yeah, you sometimes hear the distinction of supervised versus unsupervised. And this is somewhat a blurry distinction. I don't like the distinction. I don't like to think about either supervised or unsupervised, but I have to talk about it in order to call this a course on machine learning. So you should have thought about these terms. So supervised, I would say supervised methods are machine learning methods or problems where we use labels which can only be determined by a human expert, like cow happiness or karma, or something that cannot be measured in any way by a machine or a device. And methods where the labels can be determined automatically are unsupervised methods. So if you use as a label, for example, you consider a data point being a plant, and you want to predict the total amount or the number of green pixels in the image. This could be a label, but this is something you can almost directly calculate by knowing the red, green, blue values of the pixels. So you can choose as label also something that is readily available from the features. And as you already recognize from my formulation, this is somewhat blurry. So there's no clear distinction, but I would say supervised methods use definitions for labels which you only can use when you have experts like forest fire experts or biologists. Okay. Yeah, one important thing is to get a feeling of the data, always start with visualizing the data. And in the simplest case, when you have one numeric feature and one numeric label, do a scatter plot. So this helps you only in small toy examples, because in everyday life machine learning problems, you have billions of features, but maybe still only one numeric label. And for this, we have data visualization methods. So we hear in later rounds of the courses about data visualization methods that allow to represent data points with hundreds, thousands of features in a similar way as you could represent data points having only a single numeric feature in a scatter plot. So my advice is always try to visualize in some form as a scatter plot the data set you have. Okay, now I spent almost half of the lecture on data, on the first component, and from this already you might infer that actually I consider this the most important component. So the most important component, or the most important part of a machine learning problem, is often to find good data, to have a good database. So, second component of a machine learning method. As I already said, what machine learning is about, or most of machine learning, is about finding a map, a function, or a predictor, or a hypothesis. So these are all different names for the same thing. It's a rule or a function that reads in the features of a data point, like the red, green, blueness values of all pixels, and computes a label, but it doesn't compute the true label in general, because this would be too good to be true. It computes y hat. So y is the true label, but what comes out of a predictor map is an estimate or a prediction, y hat. Okay. And there are typically, so how many such predictor maps are there? Let's say we have a single numeric feature and we want to predict a single numeric label. So let's say the feature, a data point would be 1 day, and the feature is the morning temperature that I can look up from my thermometer. And I want to predict the label, which is the maximum daytime temperature. So let's say I have some data points from historic data, from a Meteorological Institute repositories. And now I want to construct or learn such a predictor. How many different predictor maps are there? In principle, infinite, yes. Is any mathematics student here? So is it infinite, or is it even more than infinitely many predictor maps? So it's even more than just infinite. It's uncountably infinite. So it's very much infinite. Really a lot of predictor maps. And this doesn't fit into a computer. So a computer like I have here, which I use now, is a laptop which only has finite number of bits, finite number of clock cycles that I can use within 1 second. So I have finite resources, and therefore we must restrict the set of possible predictor maps to a subset. And this is what we call a hypothesis space. So although this sounds very theoretic and abstract spaces, it's actually a very simple idea. It's just a subset of possible predictor maps. Let's say, instead of considering all three, I only allow for this blue dashed or this red dashed predictor map. So I restrict the machine learning problem to the hypothesis space given by these two predictor curves. Okay? And again, like for what data points are or what features or labels are, a hypothesis space is a design choice. It's up to you. There's nobody who tells you what is the right choice for the hypothesis space for your particular data set, like for the cows. So if you want to develop a system for predicting cow happiness, the farmer doesn't tell you what the good hypothesis space is. You must find that out or try that out. And we will show you some ways, some methods to explore different hypothesis spaces and choose a good one. So again, a hypothesis space is just a subset of different predictor functions. And machine learning is about choosing the best, in some sense, the best predictor function out of this hypothesis space. And in this case, so in this very simple case here on these slides, the hypothesis space just consists of 3 different predictor functions. Okay? And machine learning here would just amount to choose between 3 different hypotheses. And in general, we have way more than 3. We have basically infinite, many different hypotheses, even even if we restrict ourselves only to linear functions, there are infinitely many linear functions, but we can approximate linear functions well. However, in these courses that you now attend, we don't ask you to learn methods for choosing, for optimizing functions. We don't ask you to understand optimization methods. We will merely use ready-made Python functions that come with Python libraries like scikit-learn or keras, and which provide a function which is often called fit. And whenever you see a function called fit, also using some parameters, then what this function does is it searches the best hypothesis out of a huge hypothesis space. Okay, so the question now is, how do we define the hypothesis space? And you define it. You define it by choosing, for example, linear functions. So when you use linear functions, then this is called linear regression. This is one particular choice. And there's a Python library for linear regression. And this library has a function linear regression dot fit. Then you could say another choice for hypothesis space are decision trees or regression trees. And there, again, there's a function called decision trees or regression trees dot fit in Python. So you choose the hypothesis space. And in particular, in deep learning, we use a subclass of hypothesis spaces. So in deep learning, what sets deep learning apart from general machine learning is that we restrict our attention to a subclass of hypothesis spaces. And this subclass of hypothesis spaces is defined by, in some sense, a signal flow diagram or a flow chart, which is called an artificial neural network. So an artificial neural network is nothing but a very clever and graphical way to represent a map, a predictor map, from features to a prediction result, a predicted label. And this flow diagram is based on combining simple computational units, which we call neuron. So a neuron, a single neuron, is a very stupid thing in general. So it just sums up the inputs, weighted. So each feature here is weighted by some number, W1, W2, W3. This weighted sum here, this is the weighted sum, is then fed into some nonlinearity. This is called an activation function. And we typically use only a few different choices for this activation functions. So one popular choice is the rectified linear unit, which is shown here. Another choice is the sigmoid activation function. Okay. But you could also use, in principle, a linear function, or just use the weighted combination for the activation function. Okay, and an artificial neural network, in particular a deep neural network, is then obtained by combining these single neurons, these stupid computational units, in a network. And it turned out that a very clever or very useful way to organize or to combine these neurons is by grouping them into layers. So there's one question on the chat. What is the functional form of this activation function? Well, you can look that up in the book. So this is simple. For example, this ReLU unit is just the positive part of C, and the sigmoid, you can also find a nice closed form for the sigmoid function. I just write down ReLU. For ReLU, G of C is the maximum of C and 0. So these are very simple functions. There's not much artificial intelligence going on here. The intelligence comes from the fact that we can tune the weights here. So this is the important thing. For each choice for the weights, we get a different map. If we choose for this weight here 1, for this weight here 0, we get one particular map from feature to output. And for another choice for the weights, we get another function. So I have shown this here. So the hypothesis space that we obtain from an artificial neural network is obtained by all maps that are obtained from this artificial neural network structure but by using different values for the weights. So different values for the weights give different functions. And the set of all the functions that we can represent using a given structure is a hypothesis space. So machine learning or deep learning is then about finding the best function or finding the best choice for the weights out of all possible choices. And this is exactly what the fit function does. Okay. So the last part, and maybe the least important or the least challenging part of a machine learning problem, is the loss function. The loss function tells us how to choose the weights. So let's say we have chosen some particular weights for a neural network, and we feed in a picture, and the output is cat. So we can represent the type or the class of the image by 0 or 1 or by a label called cat or dog. So let's say we obtain for this particular data point with these features the label cat, and this is true. Yeah, but there's another data point. We apply the predictor map to another data point, which is clearly a lion, but it predicts dog. So there's an error. And the loss function is just a precise way to measure the error. So formally, a loss function is a map or a function that takes a predictor map and a data point for which we know the label and assigns a number. So this might seem abstract, but there is not much mathematics behind it. It's just a very rigorous way to define concepts. So let's look at some examples to make it more tangible. The squared error loss is one example for a loss function where we measure the quality of a prediction by comparing it with the true label, taking the difference and squaring it. That's why it's called squared error. This is one way of, one possible definition for the loss function. Another loss function is called the logistic loss, which I have shown here as a formula. And you don't have to understand or you don't have to derive these expressions here in these courses. I just want to tell you there are different choices for the loss functions, and actually it is also a design choice. So nobody tells you what is the correct choice for the loss function. You can choose different loss functions. And here I have shown a code snippet of Python for showing how you can choose the loss function. So here you choose as loss function categorical cross entropy. And yeah, there's of course one question, which is better? Which loss function is better? And I don't have an answer. This depends on your application. But I want you to try out different loss functions, at least in your student projects, and then comment on the results. The loss function is something that just is used as a vehicle or like a tool to learn a good predictor. So, because only if we define a loss function, only if we define the loss function, like here we use the squared error loss, then we can compare different choices for the weights, for example, or we can compare different predictor maps. Without a loss function, without defining the measure for the error precisely, we cannot draw such plots. We cannot optimize the weights of a deep neural network. We need to define a loss. However, some loss functions lead to poor predictors. This is something you have to then evaluate after you have trained the model using a fit function. For example, I have shown here one example. So this blue curve is the predictor map that is obtained from a deep neural network with whose weights are chosen to minimize the squared error loss. So I have chosen the squared error loss and trained a deep neural network by minimizing the difference between the blue curve and these red training points. Okay, and these data points represent minimum daytime temperature and maximum daytime temperature on a day. And so the question now is, was this choice of a squared error loss a good choice? Or a similar question, is the resulting predictor that I got from minimizing the squared error loss over these training data points, is the resulting predictor useful? Is it a good predictor? So would you use this blue curve as a predictor for the maximum daytime temperature based on the minimum daytime temperature? No. Why not? Well, on the left side here, this predictor never predicts a negative maximum daytime temperature, even if the minimum daytime temperature is very cold. So it seems this doesn't make sense. And I have seen already some comments on the chat. This is because we overfit the training data. So you will hear more about overfitting in later rounds, but just want to point out that although we have now set up a nice principle for learning a predictor, just minimize the average loss, this might fail badly in some cases. And to avoid such cases, what we need to do is called validation. So we need to split the labeled data points that we have into two subsets, at least two subsets. One subset we use to train the model. We use to tune the weights of the predictor. And after we have trained the predictor, we try it out on the other subset, which is called validation set. And this is the minimum you must do when you apply machine learning. If you don't do this, you can fall into your nose badly. So if you only use training data, training error, and go to your boss or to your customer and report great results, you might have a bad, very bad experience. This is the ground rule number one in machine learning. Always validate, okay? And I want you to do this also in the student projects and in the project report. So what I want to see from you is always two numbers. The training error, so how small could you make the loss on the training set by using a fit function to choose the weights good. And I want you always to compare it with the validation error, which is typically larger. And if the validation error is very large, then this points you to a situation like this here. So when you have a large validation error, then this might mean overfitting, and the predictor that you learn is basically useless. The only thing that you can infer from having a small training error is that the fit function works. So this might already be non-trivial. It might be non-trivial to use the fit function such that it optimizes the weights optimally. This might be already non-trivial, but from a small training error, you cannot tell more than just, yeah, the fit function works well. It fits the weights or the deep neural network or the linear model well to the training data, but it doesn't tell you more. You always have to compare the training error with the validation error. Yeah, this validation error is also sometimes called test error, and there's some confusion about this. I just want to point out this slight distinction between test error and validation error. So if you use a data set or the error on a data set to tune something like the weights, then you must use a further data set for testing or validating. So if you use the validation error, and this is actually what you should do, you should use the validation error to decide if you should change the deep neural network, if you use less layers or more neurons, or if you use a linear model, or if you use a regression tree. This is something you can choose based on the validation error. And as soon as if you use the validation error to do model selection, you use it already. And if you use a data set to tune a model, you must use another data set to test it. And then you need a test set. So in general, you need the training set to tune the weights of the model. So you need the training set to tune the weights here in this deep neural network, okay? Then you compute the validation error, and if the validation error is too large, so you compare the training with the validation error, and the validation error is too large, then you must think about changing the network structure. For example, using less neurons, making it smaller. And as soon as you do this, you need in the end a third set called the test set, because you have used now the validation set to tune the model. Okay, but you will try out this in the student projects. Okay, the most important message here now is always compare the training error with the validation error to diagnose the method. And you will learn throughout the courses now how you can diagnose the method, how you can detect overfitting, and how you can avoid overfitting by, for example, using regularization or model selection. Okay, that's what I had on my mind to give you on the way. So are there now questions? Please go ahead with questions. There's one question. Can we randomly draw from the data set to have training set tested? Yes, that's typically done. So you have data points. You have data points, like here in this case, you have 5 data points. And then you can randomly, you can, and this is done, randomly select subsets. Okay, then the question is, what if I get a smaller validation error than training error? So this should typically never happen. If you get a smaller validation error than a training error, then this might point at that the training doesn't work. So the fit function doesn't work properly. Okay. Another question, how do we understand the validation error is too big? By comparing, you recognize this if you compare it to the training error. So if the training error is, let's say, 10% and the validation error is 90%, then the validation error is too large. So you always compare it to the training error.
But you said the validation error it's natural for the validation error to be bigger than the training error by some amount. How do we understand it too big?
Yes, so ideally the validation error is only slightly larger. So we want to drive the validation error towards the training error. They should be on the same level.
That's the ideal, right?
Yes, that's the ideal. That's why we want to go with tuning the model or choosing different loss functions. Also, changing the loss function means tuning the model to some extent.
Okay.
Okay, another question. Is there a rule of thumb on choosing the training validation dataset ratio? No, there's no widely applicable rule that tells you should use 70% of the data points for training and 30% for the validation error. No, unfortunately, we don't have that. Another question, does having both training and validation error converging to one another will be optimal design choice? Yes, as I said, ideally, what we want to achieve is that the training error is on the same level or has the same value as the validation error. That's the sweet spot, so to say. Okay, another question. Can you please tell where the new data sets are coming from? Yes, that's a very good question. So acquiring more data depends on the application. Acquiring more data could mean we need databases that reach farther back. So we need historic recordings, not only from last year, but from last 10 years about the weather, for example. Or we need to use more sensor devices. A sensor could give us more data points. So this is highly non-trivial to get more data, and we might avoid this strategy. Getting more data could also help to reduce the validation error, but it might be too costly. Okay. Let's see. Yeah, can the training and validation sets intersect? Yes, that might be possible. But they should not intersect too much. So if they are randomly chosen, the subsets, then they might intersect slightly. So another question, how could we compare the validation and the training errors? Well, there's no strict rule, but in general, I would say the validation error should not exceed 50% by 50% the training error as a rule of thumb. But there is no strict formula for this. One question, how to select the best model? So we will discuss this in round 4 of the machine learning course. In general, we pick the best model by using the model with the smallest validation error. Then another question, are there some kind of hints based on initial data, which model will suit better? No. So this is something where we still need machine learning experts and where you might then find a job. So this is called auto machine learning, which just looks at the data and finds the best model immediately. And we are not there yet. So another question, how do you choose the loss function? This is trial and error. As I said, a loss function is a design choice. A popular choice for numeric labels is the squared error loss. And for binary labels like cat or dog, or 1 or 0, is the categorical cross entropy or logistic loss. But in general, you're free to choose the loss function, and you might try out different loss functions and compare them via the resulting validation errors. Okay, now, if you use linear neurons, it reduces to linear maps, and that's really not helping. Very good point, yes. So if you consider deep neural networks with activation functions being linear, what you do is you combine linear maps with linear maps. And maybe you remember from your math course, multiplying a matrix by another matrix, which is just a linear mapping, gives another matrix. So adding layers doesn't bring anything. You really need to have nonlinear activation functions to get an advantage from deep neural networks. Very good point, yeah. What is the ratio between training, validation, and test set typically? Yeah, there's a rule of thumb of 70% training and the rest validation or test, but there is no widely applicable optimal choice. So this is, again, trial and error. How to decide when to use deep learning and when to use something like linear regression? Good question. Again, this would be auto machine learning, which we don't have, and you have to try it out. So you try out deep learning, and you try out linear regression, and you compare them based on the validation error, for example. And you pick whatever has smaller validation error. So if validation error is smaller than training error, but training error is large, this is fine. No, if the validation error is smaller than the training error, then this is a sanity check that the training didn't work. So the fit function, the optimization method, and you will hear in the deep learning course, you will hear a bit more details about how we can optimize the weights. But if the validation error is smaller, significantly smaller than the training error, this points at that the fit function is somewhat faulty. Okay, using more neurons can make the output more precise. So using more neurons allows you to basically means to increase the hypothesis space. You can represent more functions using more neurons, but on the other hand, you also increase the risk of overfitting. So this overfitting happens either if you have too little data points or if you have too many weights, if the model is too complex. So many. How to pick the scattered data to train a model just randomly? Yes, often we just randomly select a subset of data and use this as a training set. Another question, are the data sets always chosen from actual past data, or they can also be future uncertain data? So the data is anything you have as bits or bytes. So it can be recordings from the past, or it can be something that has been computed based on the past, like predictions. So you could use predictions that have been computed as features or as training data for some other model. Only the sky is the limit here. How different is deep learning from machine learning? Yeah, as I said, deep learning methods are a small subset of machine learning in the sense that they only use artificial neural networks to represent maps. Machine learning in general uses any type of predictor maps, but deep learning uses artificial neural networks to represent maps. How do you get some data sets large enough to use as deep learning needs a lot of data? Well, either you have the resources to collect so many data, and in particular so much labeled data, or you reduce your complexity, or you use some regularization techniques. This depends on the application, how easy it is to collect data. As a general practice, do machine learning experts determine the best machine learning method themselves, or is it designed by some code? So as I said, we don't have auto machine learning yet, but you need to do trial and error. So try out many different choices and see what gives the smallest validation error. Another comment, is using some synthetic data in training reasonable? For example, adding noise to existing data. Yes, that's a very good point, and this is called data augmentation, and you will hear about this in a later round in both courses. Data augmentation is a very powerful way to augment, as the name says, to augment or to enrich data, to make more data out of what we have by just simulating or adding a bit noise. And this, by the way, is a cheap way to get data. So if this works, then this is a very promising and efficient approach, but it does not always work. How can we choose the nonlinear activation function? So there are a few options for this, and you can choose between them. So there's the choice of rectified linear unit, and I guess sigmoid are the main choices. And you can choose which one you want. For the deep neural network. So can there be underfitting? Underfitting happening? Yeah, underfitting can also happen. So this is a case of overfitting, and underfitting would be, for example, if I have just a straight line here. So a very low complex model, but it doesn't fit well the data. And if we have underfitting, then what could we do? What could we do to make the model more powerful or more flexible? Add more features, or use more neurons, use a larger neural network, more layers. Okay, another question, validation error or accuracy obtained from test data, which one is more reliable? Well, it depends what you want to do. When you want to compare different models, then you have to use the validation error. If you want to give your customer a performance measure for your method that you have chosen, you need to use the test data. So the test error is the number that you put into the PR material when you want to sell your method in the end. But to choose between different methods, you use the validation error. Another question, how reliable are the models if text data have much unclean stuff in it? I'm not an expert in natural language processing. There are separate courses on natural language processing. This is a very important question, but we cannot, this is out of scope of this basic course. What is YOLO in terms of ML? Don't know. In which case we use machine learning, in which case for deep learning. Again, this would be auto machine learning. If I would solve this, then I might not need to teach anymore and just live from my patent fees. So thanks a lot again. We are now at the end of this lecture. If you have any questions, don't hesitate to contact us via email or on the Slack. And yeah, have a nice weekend. Bye.